Wow. Wow. You've made it. If you have come this far, then you have made it. Session 6 is finally here. 6 weeks of teaching is finally here. Some of you thought it would never come. Even though it's 6 weeks, it has felt like the longest week for some of you, because of the nature of the semester, and then the intensity that has come along with it. Yes, it's all part of the experience. It didn't kill you. If you have come this far, then you have come thus far. Congratulations. So we will just jump into action and then have the last discussion for the semester. However, our course project continues. Maybe after my last word, I'll throw some highlights on what to expect and how you should prepare for your exams. But it's not going to be anything difficult. It's just 30% of your total continuous assessment, and I expect everybody to actually make the maximum mark in this regard. So congratulations once again. If you have come this far, congratulations, you've done so well. So we'll hit the nail on the head and then talk about section 6. Section 6. Software engineering is quite broad, and I'm just highlighting portions of some of these things. If any of you should further on your education, even at the department, to do your MPhil, you will be expected to take, there's an elective course called Advanced Software Engineering. Trust me, it will be a walk in the park. That is if you have diligently, followed through everything we have discussed so far. And then if you have also been able to take part in all the projects and forms of assessments that has ensued throughout this particular journey. I am particularly happy for you. Very, very happy for you. I'm really happy for you. I'm pretty sure you can see the delight written all over my face. Just as it marks the end of it, I'm also pretty much relieved that there will be no more recordings like this. A lot of new things has happened with you in terms of my engagement with you. Well, let me not begin to reminiscence and be all what word do we use? Sentimental, about this whole feeling. Let me just hit the nail on the head and let's move on, shall we? Great. So Section 6, Reliability Engineering and Safety Engineering. Reliability Engineering and Safety Engineering. Now we're saying that in general, software customers expect all software to be very dependable. And we made this statement clear in the last session. They all expect it to be very reliable and dependable. Now, for non-critical applications, they may be willing to accept some level of failures. Not entirely, but some level. And some applications have very high reliability requirements, and special software engineering techniques may be used to achieve this. You imagine your banking software finding out that it is so buggy, and the figures that you see are not the figures that you've been hearing about. You perform one transaction, you deposit the figure reduces. You do that, it changes. Only God knows what would have happened in this system. That is the level of trust we all have for the banking softwares, even as they go more electronic and so on and so forth. That's that level of dependability. There's some level of failures we can accept, but not in entirety. Let's look at some few terminologies, shall we? We have human errors, we have system fault, we have system error, and we have system failure. These all four mean quite different things. When we talk about human error, we are talking about the behavior that results in the introduction of faults into the system by a human being. And when we talk about system fault, we are talking about a characteristic of the software system that can lead to a system error. In the case of the system error, which is as a result of a system fault, is an erroneous system state that can lead to system behavior that is unexpected by system users. And then we can talk about system failure, which is an event. When there's a system failure, an event has occurred, and this event at some point in time, occurred when the system does not deliver or did not deliver a service as expected by its users. I guess we can relate with some of these words. So when we talk about reliability as a term, we are talking about failures that are usually a result of system errors that are delivered from faults in a system. Okay, so you take notice of that. Errors do not necessarily lead to system failures. If the error is corrected by built-in error detection and then recovery mechanism, if they are so, then errors do not necessarily lead to system failures. Okay, we are throwing more light on reliability engineering. Okay, that is the main point we are trying to drive home here. So let's look at how we can manage faults. Fault management strategies to achieve reliability. Fault management strategies to achieve reliability. So we have fault avoidance, where you develop techniques, to minimize the possibility of mistakes or trap mistakes before they result even introduction of system faults. We can talk about fault detection and removal. So after verification and validation techniques have been put in place, you increase the probability of detecting and correcting errors before the system even goes into service. That is also important. Then we have the fault tolerance, which is not the first time we are mentioning it. These are runtime techniques that are used to ensure that the system faults do not result in system errors, and or that the system errors do not lead to system failures. Okay, I hope this has sunk in pretty well. More on the reliability and then availability, since these words are interrelated. Okay, so reliability is actually the probability of failure-free system operation over a specified time in a given environment for a given purpose. And availability is the probability that the system at a point in time will be operational and then be able to deliver the requested services by a user. So both these attributes can be expressed quantitatively. So when we say that there's been an availability of 0.99, we imply that the system has been up and running 99.99% of the time. It's as simple as that. And the formal definition for reliability does not always reflect in the user's perfect perception of the system's reliability. There are two things entirely. The user's perspective is a different story in itself. So reliability can only be defined formally with respect to system specification. That is, the failure is a deviation from a deviation from a specification. So users don't read specification and don't know how the system is supposed to behave. So when we talk about perceived reliability, it is more important in practice. Availability is another word we have mentioned here, which is usually also expressed as percentage of the time the system has been available to deliver the service it's supposed to. We could say 99.95%. However, this does not account for two main factors: the number of users that have been affected and then the length of outage. So if you remove X% of the faults in the system, it will not necessarily improve the reliability by X%. No. So the program defects may be in rare executed sections of the code. So it may never be encountered by users. So removing these does not necessarily affect the perceived reliability. So users adapt their behavior to avoid system features that may fail for them, and the program with known faults may therefore still be perceived as reliable by its users in any ways. Now that's how come Sakai will always stay and will not be argued, no matter the number of students that will complain. It's quite as simple as that. Functional reliability requirements actually also define system and software functions that avoid and detect or tolerate faults in the software, and so ensure that these faults do not lead to system failure. All this, why we are just defining most of these key terms that pertains to this section of the reliability engineering. Reliability literally is therefore a measurable system attribute, so non-functional. So non-functional requirements may be specified quantitatively, and these define the number of failures that are acceptable during normal use of the system. So we have some level, a threshold of acceptability in terms of failures for every system. The fact that 1, 2, 3 people have been victims does not mean that the over 20,000 people who are equally using it and have had no issues should also fall in line with just 1 or 2 people. It means that the system is not working. No, it is working. So functional reliability requirements actually define the system and software functions that avoid, detect, or tolerate faults in the software. And so in a nutshell, they ensure that these faults do not lead to system failure in entirety. So what are some of these reliability metrics? These are literally units of measurement of a system reliability. The metrics include probability of failure on demand, POFOD, the rate of occurrence of failures, ROCOF, the availability, which we are referring to as the avail. Okay, so they are actually self-explanatory. All these three are the measures of metrics for measuring the reliability of a system. We have non-functional reliability requirements, and these are specifications of the required reliability and availability of the system using one of the metrics, either POFOD, ROCOF, or avail. Okay, so quantitative reliability and availability specification has been used actually for many years in safety critical systems, but it's uncommon for business and critical systems. So we are saying that more and more companies demand 24/7 service from their systems. And that's why people are transitioning from human beings to machines and softwares. So it makes sense for them to be precise about their reliability and their availability and expectations, as long as we have moved the human side of things and we want machines to work. We also have functional reliability requirements, just as we have the non-functional ones. And these ones specify the faults to be detected and then the actions to be taken to ensure that these faults do not lead to system failure. So we literally, by way of this check requirements that identify the checks to ensure that incorrect data is detected before it leads to failure. Recovery requirements that are geared up to help the system recover after a failure has occurred. And you also make sure redundancy requirements that specify the redundant features of the system are included. And then the process requirements for reliability, which specify the development process to be used, may also be included at this particular stage. So what is this fault tolerance that we've been talking about? In critical situations, we are saying that softwares must be fault tolerant, and it's very, very important. Those of you who extensively investigate into vMix, we even have a fault tolerant feature which you can enable, and they will give you some pop-up dialog box. You need to consent and all, but I'm not going to get into that detail for now. So fault tolerance is actually required where there are high availability of availability requirements, or where system failure costs are very, very, very high. Okay, so fault tolerance means that the system can continue in operation in spite of a software failure. That is what we are saying. Even if the system fails, the system can still proceed. So even if the system has been proved to conform to a specification, it must also be fault tolerant, as there may be specification errors or validation that may be incorrect. You can never tell. So when you have a fault tolerant, if you need to consider that, in fact, we need to focus on that in an architectural mindset. So we have the fault tolerance systems architectures that are used in situations where fault tolerance is actually essential. And these architectures are generally all based on redundancy and diversity. And here are some few example situations where dependable architectures can be used. We have the flight control systems, and we have the reactor systems, where we have this nuclear whatever. Telecommunication systems, where there is the need to have 24/7 service for users. Okay, so still on fault tolerance, we can talk about protection systems, which is a specialized system that is associated with some other control system, and this can take emergency action if a failure occurs, and that is what we're referring to here as protection system. So we have an example, a system to stop a train if it passes the red light, for example. This may be an abstract abstract example for much of the Ghanaians in this class, but pretty much the Nigerians, I don't know whether they use trains very often there, but if you're Westerner, most likely you should know what I'm talking about. A train running the traffic lights, depending on the way it's situated, a lot of things could happen. We have trains here though, but I don't know many of us patronize it. I have never patronized a train service in GH, but that's an example we are citing here, as you may qualify in the key text. Protection systems, we are saying, are redundant because they include monitoring, control capabilities that replicate those that are in the control software. So protection systems should be diverse, and they should use different they should use different technology from the control software. Okay, so it's very, very important. We have a diagram to depict fault tolerance in an environment. So system environment, we have the protection sensors, we have the sensors on the other side, we have the control system, and then we have the protection system, then we have the actuators, and then the controlled equipment at the final stage. So the arrows will tell you how the movement by and large works. So when we talk about self-monitoring architecture, we are saying a multi-channel architecture where the system monitors its own operations, and it takes actions if there are inconsistencies that may be detected. So we can have hardware in each channel that has to be diverse, so that common mode hardware failure would not necessarily lead to each channel producing the same particular results. Right, so you take notice of this. Take notice of this. Okay. Excuse me. Now we have end version programming, and this end version programming involves multiple versions of software systems to carry out computation at the same time. We are saying that there should be an odd number of computers involved, and typically we should have like 3 of them. Now the results are then compared using a voting system, and then the majority result is taken to be correct results. So technically, democracy is even applicable in software engineering. It translates beyond there. So the approach derived from the notion of triple modular redundancy is actually used in hardware systems. So what do we mean by an hardware having a fault? Hardware fault tolerance actually depends on triple modular redundancy, what we refer to as TMR. And these are 3 replicated identical components that receive the same input and whose outputs are actually compared. So if one output is different, then it is ignored, and then the component failures, it is ignored and the component failure is literally assumed. Right, so that's about fault tolerance in a nutshell. There's a expanded form of these things in the key text. Another point we need to drum home here is good programming attitude, or programming for reliability. Now, when we talk about reliability, programming for reliability, we are literally talking about good programming practices which can be adopted that help to reduce the incidence of program faults. Okay, the practice actually supports fault avoidance, detection, and tolerance. So what we literally recommend you do is that you limit the visibility of information in a program. Okay, the program, so these are steps that we recommend. The program components should only be allowed access to data that they need for their implementation. It's as simple as that. Okay, the other point is make sure you check all inputs for validity, so that all programs take inputs from the environment and then they make assumptions about these inputs. is very important. Then you now provide handlers for all exceptions, and this should guide your development. Okay, so a program exception is actually an error or some unexpected event, such as a power failure, just to mention some, to give you a picture of what we're talking about. So exception handling constructs allow for such events to be handled without the need for continual status checking to detect literally exceptions as you move on. Then what do you do next? Minimize the use of error-prone constructs. Very, very important. Minimize the use of that. Program faults are actually usually a consequence of human error, because programmers usually lose track of the relationships between the different parts of the system. And we are saying that this is exacerbated by error-prone constructs in the programming languages that are inherently complex, or that don't even check for mistakes when they could actually do so. So when you are programming, you should try your very best to avoid or at least minimize the use of these error-prone constructs. So you have the error-prone constructs, we have the unconditional branch or go-to statement, we have the floating point numbers or inherent precise, which may lead to invalid comparisons, and then we can talk about pointers as well. All of these are concepts you have studied before. Now, after minimizing the use of error-prone constructs, you can also minimize, we can talk about, okay, so just still under the same construct, we have several of them. Aside from the pointers, we can make mention of dynamic memory allocation, parallelism, recursion, interrupts, inheritance, aliasing, unbounded arrays, and the default input processing. All of these things are measures that you can leverage on to minimize the use of error-prone constructs. Then the next stage, you provide start capabilities. Is very important. You provide restart capabilities. So for systems that involve long transaction or user interactions, you should always provide a restart capability that will allow the system to restart even after a failure, without users even having to redo everything that they have done. So that is very important. That's very important. Then in some programming languages like C, it is possible to address a memory allocation outside the range allowed for in an array declaration. Okay, so in a nutshell, all I'm saying is let's also include check array bounds. Let's look at check array bounds in your programming. All of this is programming for reliability. If you can do these things, a lot of trust will be reposed in your solution. Okay, so aside from this one, you can also include timeouts when calling external components within a particular space of time. If the response is delayed, you can just turn it into timeout, because the period within which the request is still being expected, don't forget your ports are open. You are exposing your application, you are exposing your servers. A whole lot of things can be discussed in there. So in a distributed system, failure of a remote computer can be silenced, so that programs expecting a service from the computer may never receive that service or any indication that has been a failure. So even with respect to the clients you are having and the software you are developing for them, you may go into production, especially those of you who have broken the project into phases and communicated this to your clients. It will be important for you to, even when you create the menu, the page shouldn't run into the error code as to be interpreted by a developer. It should rather translate into a form that will indicate that maybe we should be expecting the message, something, So if there's a long delay, don't forget to clear and implement a timeout in that regard as well. So these are some of the suggestions we have for you. Try to also name all the constants that represent real world values. Name all of them. Don't go and use some X and Y. If it is for a particular purpose, put that rightful name on it. Always give constants that reflect real world values, like tax rate, renames that rather give them these names rather than just using numeric values and always referring to them by name. You less likely to make mistakes, and type in the wrong value when you are using them. So that's another one. That's just, I think, the last item as far as programming for reliability is concerned. We'll move straight on ahead and talk about safety engineering, since that is quite brief as we bring the session to a close. Safety is no new word in your vocabulary, a property of a system that reflects the system's ability to operate normally or abnormally without danger of causing harm, human injury, or possibly even death, and without damage to the system's environment. And it's important to consider software safety, as most devices whose failure is critical now incorporate software-based control systems. Software and reliability are actually related, but frankly they are distinct. Reliability is concerned with conformance to a given specification and delivery of service, and safety is concerned with ensuring system cannot cause damage irrespective of whether or not it conforms to specification or not. Okay, so system reliability is actually essential for safety, but the fact is that it is never enough. So reliable systems can be unsafe under some of these conditions: dormant faults, specification errors. Dormant faults when a system can remain undetected for many years and only rarely arise. Specification errors when the system can behave as specified but still cause an accident. Hardware failures could generate spurious inputs that are hard to anticipate in the specification, and we have the context sensitive commands that are often the result of an operator error. So in the safety critical system, it's essential that the operation is always safe. When we say it should be safe, we mean that the system should never cause damage, to people or the environment in which they find themselves. We can liken this to an aircraft, process control systems in the manufacturing industry, the chemical manufacturing industry, and then the automobile control systems and all. So there are two actual levels of safety, criticality. We have the primary and the secondary. The primary safety critical systems have embedded software systems whose failure can cause the associated hardware to fail and directly threaten the people. And in the secondary instance, the system's failure resulting in the fault in other systems, which can then have safety consequences. So we have some few safety terminologies that I will leave you to go and look at. Accident, hazard, damage. They are kind of related, but never the same. They are not even synonymous. You may want to know. So how do we achieve some of these safety strategies? You can avoid hazard. If you can have a hazard detection and removal in place, or you can minimize your damage, then you can achieve some of your strategies as far as safety engineering is concerned. So safety engineering strategies, when we talk about hazard avoidance, we are literally talking about a system that is designed so that some classes of hazard simply cannot arise. And when we say the detection and removal, they are designed so well that the hazards are detected and removed before they result even in an accident. And then the damage limitation, I've already made mention of that. So accidents in complex systems rarely have single cause. There are always consequences of other events that will result in that. So it is probably the case that anticipating all problem combinations, especially in software control systems, is impossible to achieve complete safety. It's impossible to achieving complete safety, and then that's the point we need to drum home. Accidents are inevitable, no two ways about it, but it does not change the goalpost as far as safety engineering is concerned. The main goal of safety requirement engineering is to identify protection requirements, and then ensure that the system failures do not cause injury or death, or even environmental damage in general. We can talk about a lot more examples in this regard, but we'll just leave it here. When we talk about functional safety requirements, we are talking about checking and recovering features that should be included in a system, and the features that provide protection against these system failures, and then the external attackers. So how do we have a hazard-driven analysis then? Having spoken about this at length, we can talk about hazard identification, where we identify the hazard that may threaten the system. And then we can talk about the hazard assessment, the process through which we try to understand the likelihood that a risk will arise. Okay, so we have intolerable, we have the ones that are as low as reasonably practical, what we refer to as the ALARP, and then we have the acceptable threshold as well. So the acceptability of a risk determined by human, social, or political consideration is what referred to as the hazard assessment. We have room to contain some level of acknowledgement as far as hazard assessment is concerned. And so we have the acceptability range, and then that helps create a standard or a barrier or a ceiling, let me put it that way, to which the solution can be accepted as far as hazard detections are concerned. So that's important. The process stands where for each identified hazard, there is an assessment of the hazard probability. Then we check the accident severity, we estimate the risk, and then we now determine the acceptability. Okay, so the analysis is actually concerned with discovering the root causes of the risk in a particular system. Okay, so the techniques have been mostly derived from safety critical systems, and they can be inductive, bottom up, just to mention these two. And they usually start with a proposed system failure, and then they assess the hazards that could arise from the failure. So at that point, we are talking about deductive and then top down. And they can start by this. We are starting with hazard and deducing what the causes of the situation might have been. So we can have a fault-free analysis. I don't know why I wrote fault-free analysis, which is a deductive top-down technique. Okay, so these are about three of them. We have the inductive top-down, deductive top-down, and a fault-free analysis, which is a deductive top-down technique. Okay, the whole point is to try and minimize risk. So the aim of risk reduction is the process to identify dependability requirements, accidents, incidents that do not arise. I always say that a threat is different from an attack. A threat is the potential of a risk resulting in a harmful action, and then that becomes an attack in this sense. So risk is just to know the threshold, something that has not arisen yet. So risk reduction strategies could be hazard avoidance, hazard detection and removal, and then damage limitation. Okay, so what we're saying is that safety engineering processes are based on reliability engineering, and here too regulators may require evidence that safety engineering processes have been used in a system development. Unfortunately, most solo software engineers, so-called software engineers in Ghana, freelance and don't meet any of these requirements. So we have agile methods that are not usually used for safety critical engineering. We have extensive process and product documentation that is usually needed for system regulation, as they could contradict the focus of agile methods on software itself. So there must be a detailed safety analysis of a complete system specification, and that is very important. It's very important. It will interleave the development of the system specification and then the program. So that is a point that must be well noted. Then we talk about process assurance. Process assurance, which involves defining a dependable process and ensuring that this process is followed through to the very end. So the questions we try to answer is, do we have the right processes? Are we doing the processes right? So process assurance is actually very, very important for safety critical systems development, So we need to take notice of that. So we're saying that the process assurance is actually important for safety critical systems development. And these are some of the activities that are related to a safety related process activity. One, creating the hazard logging and monitoring system. And then the two, appointment of the project safety engineers who have explicit responsibility for the system's safety. Creating a safety certification system where the safety of critical components are formally certified, and then having a detailed configuration. Okay, right, then we can talk about formal methods also under safety engineering process, and this can be used when a mathematical specification of the system is actually produced. They are the ultimate static verification techniques that may be used at different stages in the document, process. So literally, when you factor in formal methods, it will help you discover specification errors and omissions that might result. There are merits and demerits of this, which we cannot ignore. So if you produce a mathematical specification that requires a detailed analysis of requirements, then this is likely to uncover errors in the case of the formal methods. Concurrent systems can also be analyzed to discover race conditions that might lead to a deadlock. There are several others, like testing for system problems is very difficult, and they can detect implementation errors before even testing when the program is analyzed alongside the specification. And of course, the demerits is where we require specialized notations that cannot be cannot be understood by domain experts. So it's very expensive to develop a specification, and even more expensive to show that the program meets that particular specification. Proofs may contain errors, and it may even be possible to reach the same level of confidence in a program more cheaply when you use the VMV technique. So we have several other approaches to getting this out of the way. We talk about model checking, which involves creating an extended final state model of a system. The model checker will literally explore all possible parts through the model, and then to check that the user specified property is valid for each part that it will detect. So when we talk about static program analysis, this literally uses software tools for source text processing. So they pass the program text, and then they try to discover potentially erroneous conditions and bringing these to the attention of the VMV team. And they are very effective as an aid to inspections. So we need to take notice of that. There are three levels of static analysis. We have the characteristic error checking, we have the user-defined error checking, and we have the assertion checking. The characteristic error checking is a static analyzer that can check for patterns in the code that are characteristic of errors, And then the user-defined is the one instance where the users of a programming language define error patterns. So by this, they are extending the types of error that can be detected. And then the assertion checking, where developers include formal assertions in their program, and then relationships that must actually hold. So in brief, we're saying that static analysis is actually particularly valuable when the language such as say C is used. It has a weak typing, and hence many errors are undetected by the compiler. So instances like that, it becomes necessary to implement concept of safety engineering, as for that matter, static program analysis. Ladies and gentlemen, as I already indicated, it's been a pleasure coming your way throughout this semester, putting these videos together presenting them to you is actually the first of its kind, going through entire semester in this manner. But we all understand the times we find ourselves. Thank you very much for your cooperation, meeting me halfway. You have eternal access to all these links and videos and resources, as long as you can keep these links, because they remain not public, just unlisted. If you want a session for me to walk you through how I put these packages together, the video and our equipment, like I said, they are very cost effective, buying nothing new. The phone that I use and the laptop that I own, and I have a mouse, and that's all. Microphone is not necessary. You just need to find a quiet space and you can make it happen. It's been a pleasure coming your way once again. It's been an honor being your lecturer for this journey. The impact is what actually matters. I have a ritual of not exceeding my teaching week. So as long as it ends this week, that's the end of the session. However, the university has given us a directive to give you additional more weeks to complete assignments and tasks. And that's how come the course project will also continue. Your last mentorship session will also be for this week, where we meet the Microsoft engineer, the second female, and engage with that person. So beyond this week, it's just you and your teams. No further assignments. Of course, this week you will complete individual assignment for me, or not guaranteed yet, as at the time of watching this video. Anything could happen, but definitely whatever will precede the subsequent weeks is just your course project, trying to complete it with your team and submitting what I need from you when the due times arrive, and then completing the surveys. Exams is not going to be anything complicated. I call it a bonus. I'm trying my best to make it all strictly MCQs. Give it your best shot when the time comes. I wish you the very best. And once again, thanks for having me. I wish you all the best once again. I can't stop saying that. This is the end of the road. I just hope there will be no casualties, so we don't have to engage again in another year or another session. Thank you.